Bismillah, we continue our discussion on curve sketching. Today we'll be talking about asymptotes. We'll discuss both vertical asymptotes and horizontal asymptotes. First of all, to start our discussion with vertical asymptotes, suppose we have a function f of x, and we have that we call a line x equals a vertical asymptote if it satisfies limit of the function f of x as x approaches this a from the left is equal to plus or minus infinity, or limit as x approaches a from the right, f of x is equal to plus or minus a. Suppose we have a function which is rational, meaning that I have a polynomial in the numerator and a polynomial in the denominator. In such case, the vertical asymptotes will be the zeros of the denominator q of x. Okay, so let's take an example. Suppose I have a function f of x is equal to 5x, for instance, minus 3 over x minus 1. We can see that this is a rational function. Now, what are the zeros of the denominator? X equals 1. This is our vertical asymptote. Next, we move to discussing horizontal asymptotes. For horizontal asymptotes, we call a line y equals b a horizontal asymptote if and only if it satisfies one of the following: limit of f of x as x goes to infinity is equal to b, or limit f of x as x goes to minus infinity is equal to b. In such case, this will be our horizontal asymptote. Now, let's take an example and we ask you to find both vertical and horizontal asymptotes. Example, given f of x equals x squared minus 4x divided by x squared minus 4x plus 3. Can we find the vertical asymptotes and the horizontal asymptotes? Yes, for sure. We apply what we discussed right now. What are the zeros of the denominator? We have x squared minus 4x plus 3 equals 0. This can be factored. X minus 3, x minus 1 equals 0. So from here we have the zeros of the denominator to be x equals 1, yes, and x equals to 3. So these will be the vertical asymptotes. What about the horizontal asymptotes? For the horizontal asymptotes, as we discussed above here, we have to take the limit as x goes to infinity of the given fraction, rational function, x squared minus 4x divided by x squared minus 4x plus 3. We can see that the power in the numerator is equal to the power of the denominator. In such case, the limit is equal to the coefficient of the numerator divided by the coefficient of the denominator. The leading coefficient here and the leading coefficient here is 1 and 1. So our answer will be 1. So y equals b equals 1, y equals 1 is our horizontal asymptote. Now we'll do an example. Given y equals 1 over 4 minus x squared, and y prime equals 2x over 4 minus x squared all squared. And y double prime is given to be 2 into 4 plus 3x squared divided by 4 minus x squared all cubed. We will be asking you to sketch the graph of this function. In order to sketch the graph of this function, we follow the following steps. Step number A, we want to find intercepts. So I ask you to find the x-intercept. In order to find the x-intercept, we should put y equal to 0. So we have here y is never 0 because the numerator is 1. Is never 0 for all x. Next, the y-intercept. We should put x equals 0 and find the corresponding y. When x equals 0, the y is equal to 1 over 4. So the y-intercept is the point 1, 0, and 1 over 4. And this we will be using it later. Next, we need to find the intervals on which the function is increasing or decreasing. Of course, we know that in order to discuss such a thing, we need to have the y prime equal to 0. And then putting y prime equals to 0, we all see that the y prime in front of us is here. So this tells you that x equals 0. If y prime is 0, x has to be 0. Also, we have something that the y prime is undefined at x equals plus or minus 2. So originally, the given function has a domain. We should write the domain of the given function. The domain is equivalent to all real numbers except what makes the denominator 0 except plus or minus 2. This is our domain. So, yes, we have y prime undefined at plus or minus 2, but these do not belong to the domain of the function which is given. So, we cannot call them critical values. Next, what shall we do with these points that we got? We take them to the real line. And we start studying the sign of the first derivative to the left and to the right of minus 2, 0, and 2. This is minus infinity, and this goes to plus infinity. On the first interval, from minus infinity to minus 2, the second interval minus 2 to 0, 0 to 2 is the third interval, 2 to infinity is the fourth interval. Let's agree that everywhere for all x, the denominator of y prime is always positive. So we have 2 times bracket over anything which is always positive. Positive, 2 times a bracket. 2 times a bracket, positive, 2 times a bracket, positive. Now, we take anything less than minus 2, let's say minus 4, so we will have a minus sign here, so everything is minus. So wherever we go in this interval, the first derivative is less than 0, tells us that the function is decreasing. Next, minus 2 and 0. We take minus 1, again we have a minus, we still have a minus. The f prime is still less than 0, so the function is also decreasing here. Next, we take a value between 0 and 2. Yes, this is 1, for instance, 1.5. Anything we take here is positive, so the whole thing is positive, telling us that the first derivative is positive in this interval, tells us that the function is increasing in this interval. We take something greater than 2 in the interval from 2 to infinity. Let's take 5. This is positive. Again, everything is positive here. F prime is always positive in this interval. So we have F prime is greater than 0, tells us that the function is increasing on this interval. So we are able to find the intervals on which the function is increasing and decreasing. Next, we are asking you to find critical values. We already did. The critical values are now known. Can we say that the plus and minus 2 are critical values? No, they are not, because they don't belong to the domain of the function. Only we have x equal to 0. Next, we want to know relative extrema. So relative extrema, so we're talking about relative minimum or maximum. As we see, the only point here we can talk about it having relative extrema is the 0. We can see that the function is decreasing to the left of 0 and then it starts to increase. So at x equals 0, f, which is equal to 1 over 4 minus x squared, has a relative minimum. So f minimum is equal to f of 0, which is equal to 1 over 4. So the point 0 and 1 over 4 is the point where where the function has a minimum value. Relative minimum. Next, we need to study the concavity for this function. Concavity. And we need to find points of inflection if they exist. It can be a point, it can be more than one point, if existing. Okay, in order to study concavity, as we said last time, we need to study the second derivative. And we have the second derivative given up here. Again, y double prime is equal to something cubed, which is 4 minus x squared over, and in the numerator, we have 2 into 4 plus 3x squared. So we should say y double prime, can it at all be equal to 0? We can see that this is squared plus something which is positive, so the numerator is never 0, so y double prime is not 0 for all x. What about y double prime being undefined? Is undefined at x equals whatever makes the denominator 0 plus or minus 2. And again, we have to say that these two values do not belong to the domain of the given function f. Okay? So again, we go to the real line. We put the minus 2 and the 2. And we study the concavity, which is we study the second derivative, the sign of the second derivative. Now, we all agree that the numerator is 2, positive, and this bracket, everything is positive, so we have a positive numerator, but a denominator which is being cubed. A positive numerator and a denominator which is being cubed. Again, a positive numerator and the denominator is being cubed. I start taking values from each interval. The first thing, I will take a value in the first interval, which is from minus infinity to minus 2. If I take minus 10. Minus 10, when you square it, it's 100. 4 minus 100 is minus. Minus being cubed, is the whole thing is minus. So it tells us that the second derivative in this interval is negative. When the second derivative is negative, then this function is concave down. Next, we take a value between -2 and 2. The easiest of all is the 0. When you plug in the 0 here, you will get 4, which is positive, and you cube it, then this is positive. The whole thing is positive, telling us that the second derivative in this interval is positive, meaning f double prime is greater than 0 here. When the second derivative is positive, the function is concave up. And now we go to the interval from 2 to infinity. We take any value, let's say take 10 again. 4 minus 10 squared, again, the whole thing is negative. Negative being cubed is negative, so I get a minus value, so a negative value. So here we have the second derivative being negative on this interval, telling us that the function is concave down. Now, let's say we can see that the concavity is changing to the right and left of -2 and to the right of and left of 2. Can we say that -2 and 2 form coordinates, x coordinate of a point of inflection? No, we cannot, because again, this is very important here. So no points of inflection. Why? Because a point means that we need to find the y coordinate. And whenever we take the 2 or the -2 and we go to the original function up here, this makes the original function undefined. So you cannot find the corresponding y. So here we do not have points of inflection. Okay, now we will ask you a new question. Find the vertical asymptotes and the horizontal asymptotes. And as we know, the vertical asymptotes, we can get them from the zeros of the denominator of the original function. So back to the original function, the zeros of the denominator of the original function, 4 minus x squared equals 0, tells us that the zeros of the denominator are x equals -2, x equals +2. What about the horizontal asymptote? The horizontal asymptote, as I told you, you should take limit as x goes to infinity of the original function 1/4 minus x squared. If you take a limit here, what's the degree of the numerator? It is 0. What's the degree of the what's the degree of the numerator? It is 0. What's the degree of the denominator? It is 2. So here we have the degree of the denominator is bigger than that of the numerator. So this is equal to 0. So we say our horizontal asymptote is y equal to 0. Now we got the vertical asymptote, we got the horizontal asymptote. And we should collect all the information we found in A, B, C, D, E, and F and put it on the graph. Okay, so together we will draw X and Y axes. This is the Y axis. And this is the x-axis. Now we should put the points and the asymptotes we got. The first thing we got was the intercepts. So did we have any x-intercept? We said no. There are no x-intercepts. The curve is not cutting the x-axis. What about the y-intercept? We have 0 and 1/4. So if we go up, this is 0 and 1/4. If we put it here, this is 0 and 1/4. Next, what should we put? We should put also the vertical and horizontal asymptotes. We have, this is 1, this is 2, this is 1, this is 2. We go to -2, And this is our vertical asymptote at -2. Next, this is 2 here. We put, this is our other vertical asymptote. We can just say this is x equals 2, and this is x equals -2. And of course, we know that there is a horizontal asymptote y equal to 0. So 0 and 1/4 here. Very good. What's next? We should start thinking of the behavior of the function near the asymptotes. So I have y equals 1/4 minus x squared. When we get closer to -2 from the left, say I take a value which is -2.1, and I plug it in here. Do you expect the sign to be plus or minus? Yes, it's minus. So I know that as x goes to -2 from the left, we will go, the y will go to infinity. So, and if it goes to -2 from the right, it also goes to infinity. But which infinity? Plus or minus infinity? Let's do it again. I'm getting closer to -2 from the left. I take a point -2.1. I plug it in here. I get a minus value, so there should be a minus sign here. So now I know that the end part of my curve should be here, going to minus infinity. Okay, when we get closer to -2 from the right, getting closer to -2 from the right, so I take a value which is -1.9. If I plug -1.9 in this here, I will get something positive. So we have a plus sign here. So to the right, when we get closer this way, there is a terminal part here. Next, we do the same trick here. As x goes to 2 from the right, 2 from the left, we know it's infinity. But which infinity? Plus or minus infinity? Just go ahead in your original function, 1/4 minus x squared, and take something close to 2 from this side, which is 1.9. Again, if you take the 1.9 and plug it in here, you will get a positive. Okay, so as we get closer to 2, our end part is, terminal end is here. Now let's go to 2 from the left. We get closer to 2 from the left, so we are talking about 2.1 or 2.2, something more than 2. If you plug it in here, you will get a minus sign. So this will be the terminal part for your curve. Now let's remember what happened in increasing and decreasing. We all know that in this interval from minus infinity to -2, the function is decreasing, and after -2, still the function is decreasing. Okay, so we have a horizontal asymptote having the terminal ends here. Our function is decreasing, so I will start connecting the ends. Now, can we see? Yes, it is decreasing. Beside being decreasing, can you see the concavity? Yeah, it looks concave down. Let's go and see the concavity. To the left of -2, yes, it was concave down. Can we all see here? In our previous page, yes, it is concave down. Expected, okay? Now, what's happening here? The function will continue to decrease, as we said, from -2 to 0. From -2 to 0, we will continue decreasing, and this is an intercept. So we'll go here. And then after 0, the function starts to increase. After 0, the function starts to increase, and it will continue increasing for infinity. So we go like this. Yeah, we continue joining this. See, you can see the function is increasing. And at the same time, between -2 and 2, it's satisfying the condition of concavity we found here. It is concave upwards. After 2 years, expecting something which is increasing, Yes, and concave downwards. Again, after 2, yes, the function should increase and still it is concave downwards. And there we go. This is our graph sketched in yellow color. Thank you very much.